Hello everyone, this week we're going to be doing our experiment 6, which is hydrolysis of wintergreen oil under basic condition. Wintergreen oil is a ester. Okay, so for the purpose of our experiment, convert wintergreen oil into salicylic acid using aqueous base. So you will learn in this experiment how to hydrolyze an ester using a base. Sodium hydroxide is our base, and reflux a reaction, perform a vacuum filtration. So you guys can read about the background and the discussion about the ester saponification. So everything is given here, and you can also use some of this information to write your discussion. Okay, and we're going to be hydrolyzing it under basic condition. So basically, saponification refers to the process of converting carboxylic acids to carboxylate salts. This process is commonly used on long chain acids in order to form soaps. After saponification, the dianion will be recovered by acidifying the solution. So we will first do the saponification, which is hydrolyzing the ester under basic condition. That will give us a carboxylate salt. And then we're going to be adding an acid to convert it back to the acids. Okay. So in this experiment, we're going to be using first wintergreen oil. So wintergreen oil is this molecule, not that one, we have over here. Okay, so this one right here, that is the wintergreen oil. And then you use our base sodium hydroxide, and we use 2 equivalents of base. So why do we need 2 equivalents? Because there are 2 sites that a base can react. So first place is this hydroxide group over here. In the presence of a sodium hydroxide, it will become sodium salt of the wintergreen oil. And then the second equivalent, which is the second sodium hydroxide, will be used to hydrolyze the ester part. And so this process is called the saponification, and then we will be getting the sodium salt of the wintergreen oil. Okay. And then in the second step, what we are going to do is we're going to be adding hydrochloric acid over here. So that way, so the 2 salts, you see, carboxylate anions will be converted to salicylic acid, and this is salicylic acid. Okay. So we want to make sure that we make our solution really acidic, at least around 2-3 in the pH range. pK value of salicylic acid is 2.98. So we want to make sure pH is lower than this pKa, just to maximize the salicylic acid formation. Okay. After you form the salicylic acid, we're going to cool the reaction mixture in an ice bath, and then we're going to collect the salicylic acid by vacuum filtration. Okay. So let's see how we are going to perform the experiment. And these are some information about the wintergreen oil and the salicylic acid. Molar mass is given. Also, it's a solid, so you don't have a melting point. No, wintergreen oil methyl salicylate is a liquid. Salicylic acid is a solid. Okay, wintergreen oil methyl salicylate, which is a liquid. Molar mass is given. There is no melting point since it's a liquid, but we can have the boiling point for that. Density of wintergreen oil is also given. Salicylic acid is going to be a solid, and the molar mass given, melting point also given to you. You can use this information, the molar masses, to find out the theoretical yield and also and afterwards percent yield. Okay. So how are we going to perform the experiment? You can watch the virtual video, and it will show you how to perform the experiment. You're going to be adding 10 millimoles, which is 1.52 grams of methyl salicylate, to a 50 milliliter round bottom flask, and then you're going to add sodium hydroxide, about 15 milliliters, 6 molar sodium hydroxide, and then you will reflux this for about 30 minutes. And during this time, at the very beginning, it would be a white solid or a cloudy solution. It's not going to be completely soluble at the beginning. But when you reflux the reaction mixture for about 30 minutes, you will see the reaction flask becoming clear. Okay? Because at the beginning it is wintergreen oil, which is organic compound, so it's going to be insoluble in sodium hydroxide, because sodium hydroxide is a aqueous solution. When you put organic compound, they are not going to mix with each other. But when you do reflux, meaning you give heat and then you let it boil while keeping the solvent inside, so now during that process, when you add sodium hydroxide, ester will hydrolyze, and what you're going to see after 30 minutes is this dianion of wintergreen oil. So both of these are now have ionic character. It's not an organic compound anymore, it's an ionic compound. Now that is going to be soluble in sodium hydroxide. So that is the reason why you see a clear solution after 30 minutes. That indicates us that the reaction has gone to completion. So if you see still some more white cloudiness in your reaction flask, you can go ahead and reflux another 10 to 15 minutes, but mostly 30 minutes would be enough. Okay, so you do that. After you do that, you're going to cool it down to, where you can handle it safely, and then you're going to transfer this into another Erlenmeyer flask. Okay, now you have the dianion, which is the salt. What you're going to do next, okay, what you're going to do next is you're going to be adding hydrochloric acid. You will see all of this in your virtual video. You add hydrochloric acid. No, we're going to be adding sulfuric acid. It's okay, both of them are concentrated acids. So the procedure says you're going to be adding sulfuric acid, 3 molar, about 16 milliliters. And when you keep on adding it, you will see that it will start forming a precipitate. Okay, because now at the beginning, before you add your sulfuric acid, it's a dianion is what you have in your reaction flask. Now you keep on adding sulfuric acid, what's going to happen is it's going to convert to the salicylic acid. Salicylic acid is going to be organic compound. Now it will be precipitate out from the aqueous solution. Now it will become completely white solid. And then after you keep on adding, and then you're going to check the pH to make sure pH is around 2 or so, and then you're going to transfer the flask into ice bath to maximize the product formation. Then you do the vacuum filtration, let it dry, and get the melting point. Okay, so that's how you're going to be performing the experiment. Pre-lab questions. Draw a reaction mechanism for the conversion of wintergreen oil into salicylic acid. Now you need to know how to do the mechanism, and we are doing this under basic condition, and this is our wintergreen oil. So it has an alcohol functional group, and also it has a ester functional group. Okay, so let's see how to do the mechanism for this one. So you will have this OH, and then you have ester group OCH3. So you are doing it under sodium hydroxide. So what's going to happen is first hydroxide, so the most acidic hydrogen, the base will react with this hydrogen and form acetate and form the phenate anion. Okay, so you will be getting something like this with the first equivalent of sodium hydroxide, COOCH3, and then the second equivalent of the hydroxide. What's going to happen now is this is go ahead and attack the carbonyl carbon. So then the pi bond breaks and you will get this product, O minus Na plus O minus Na plus OCH3 and then the OH group. Okay, so the counter ion sodium will be here. And then what should be the next step? Next step, and what we are going to do here is a hydrolyze ester. Okay, so this is just a single bond over here, don't get confused. Okay, so what's going to happen next is, so oxygen lone pair going to form a bond so these are all single bonds, okay, 4 single bonds, and this is oxygen. So the oxygen forms a pi bond and then it leaves the methoxide anion. Okay, this is sodium right there, and now what you're gonna get is you have this molecule, oxygen, and then from the other side we have this group, carbonyl group, OH, O minus, Na plus, and then we have the methoxide ion plus the methoxide ion that leaves. So this methoxide ion, or another equivalent of sodium hydroxide in the medium, can go and grab this hydrogen. So after the end of the sodium hydroxide reflux, what we will have in the reaction flask is this anion, carboxylate anion, O minus. This is what we're going to have. Okay. Okay. So we are not done with the mechanism yet. So what should be the next step? So the next step is going to be when you add hydrochloric acid or sulfuric acid, you add HCl or sulfuric acid. Let me go ahead and write sulfuric acid since the procedure gives us the sulfuric acid, H2SO4. So this is, both of these anions grabs hydrogens, H plus ions, from the hydronium ions and form salicylic acid, which is this OH, OH. And this is the ester hydrolysis at the basic medium. Okay, so the second step happens when you add sulfuric acid, but it will stop here with the sodium hydroxide as a sodium salt. And then the next problem, if you wanted to take an IR spectrum to confirm that the reaction worked, what would you look for in the spectrum? So if you look at our starting material, which is the wintergreen oil, we have an ester carbonyl group, we have an alcohol. So now in our product also we have one alcohol group, and also we have carboxylic OH group. So both of the starting materials, we should have hydroxyl groups, which is a broad band in the IR around 3300. And both of these also have carbonyl groups. Okay, one thing that you would see maybe in the IR spectrum, the carbonyl frequency. Carbonyl frequency between the two, carboxylic acid and esters, they are not going to be that much difference, but there would be a slight difference between the two carbonyl groups of the, so this is one and this is one. Another difference that we can see here, you see here that you have a bond between oxygen and carbon, this single bond. And here we don't have that oxygen and carbon, it's oxygen and hydrogen. So you should be able to see that the disappearance of that peak, that the single bond between the carbon-oxygen peak. Okay, and also you can see what are the other differences in your starting material and the product, and see what are the kind of differences that you would expect to see in the IR spectrum. Okay, and then determine the theoretical yield and percent yield. We have done how to calculate the theoretical yield before. So our product is salicylic acid and our reactant is wintergreen oil, and you consider wintergreen oil as the limiting reactant. And in the procedure it says 10 millimoles of methyl salicylate used. So since the reaction ratio is 1:1, then the salicylic acid also you will be making 10 millimoles. And then you can convert this 10 millimoles of salicylic acid into the mass by using the molar mass of salicylic acid. And we talk about how to convert the millimoles to moles and then to the mass using the molar mass. So you can do that, and that's going to be your theoretical yield. And then the actual yield is going to be the amount you're going to get from the virtual lab, and then the percent yield you can find out actual lower theoretical times 100. I will let you do the calculations for that since we have done similar calculations before. And number 2, it is also possible to hydrolyze ester under acidic conditions. Draw a mechanism for the acid catalyzed conversion of wintergreen oil to salicylic acid. Now we learned about the base catalyzed one. So let's see what's happening in the acid catalyzed mechanism. Again, we can go ahead and draw. So this is going to be our wintergreen oil. Now in the base, what happened was base went and grabbed the hydrogen from the alcohol functional group. Then the base attacked the carbonyl carbon. Okay, now in the presence of H+, what's going to happen? So this carbonyl oxygen will get protonated. Correct? So this is going to get protonated, and this will give us the protonated carbonyl group. Nothing will happen to this phenol OH. Now this would become positively charged OCH3. Then what do you think would be the next step going to happen? So the next step, so when you say we have an acid, there are plenty of water molecules. So what's going to happen is now we have an activated carbonyl group. So the water molecule, if the carbonyl oxygen is not get protonated, water is not a good nucleophile to attack. But now that oxygen has a positively charged, so water molecule can act as a nucleophile and it gonna attack the carbonyl carbon, giving you this intermediate OH. And then we have OCH3 and OH. Okay, acid catalyzed hydrolysis of ester is a reversible process, whereas the base catalyzed hydrolysis is irreversible. Okay, once once the carboxylated ion is formed in the base catalyzed hydrolysis, it cannot undergo nucleophilic addition, the carbonyl carbon. But the acid catalyzed hydrolysis is reversible. Okay. Now at this time, now you have two hydroxyl groups and a methoxy group, and all of these oxygens are equally capable of protonating these oxygens. But since we want the reaction to go forward, what we're going to do is we're going to make the methoxy oxygen protonated by another H plus in the medium. Normally these H pluses are found as hydronium ions, H3O plus. So it goes and take up this hydrogen ion, and then what we're going to get is this intermediate OH OMe. Now this has a hydrogen on it. Now since oxygen has 3 bonds, what's going to be the formal charge of oxygen? That would be plus. What do you think is going to happen next? So the lone pair, one of these oxygens, lone pair going to form a double bond, a pi bond, and now we have a good leaving group, which is going to be a neutral methanol molecule. So this is going to form this intermediate, which is going to be this one. Which now this has a positive charge, have oxygen having 3 bonds, and then another water molecule from the medium comes in and grab this excess hydrogen and gives us the salicylic acid. Plus hydronium ion, H3O plus. So that is the hydrolysis of wintergreen oil to give you salicylic acid under acidic condition. Okay. Okay then, that's about it. I will talk to you guys later then. Bye-bye.